So in this video we're going to talk about molecular polarity. Now a lot of this comes out of the shapes of molecules. So if you didn't watch the previous video on VS-EPR theory and shapes of molecules, you might want to watch that first because you really need that information to be able to understand polarity. But covalent molecules can be described as either polar or nonpolar. This boils down to being a question of symmetry. A nonpolar molecule is symmetrical around the central atom, and a polar molecule is not symmetrical around the central atom. So I got some rules for you here that will help you decide whether a molecule is polar or nonpolar. So first of all homonuclear diatomic molecules are nonpolar. So for examples, things like hydrogen, nitrogen, oxygen, fluorine, chlorine, all these are diatomic, right? Dia means two, and homo means the same. So we have two like atoms bonded to one another. So for example, in our first example, hydrogen, we have a hydrogen atom bonded to a hydrogen atom. Well, we can't say that this hydrogen atom is different than this one. One hydrogen atom is the same as the other. So that bonding electron pair is going to get shared evenly. So as a result, it's going to be symmetrical. The electron distribution is symmetrical, and the molecule is going to be nonpolar. Okay? On the other hand, all heteronuclear diatomic molecules are polar, right? So now we're still talking about diatomic molecules, two atoms. Now we're talking about heteronuclear. The two bonded atoms are different. So let's look at the first example. We have a hydrogen bonded to a fluorine. Well, a fluorine atom is very different than a hydrogen atom. Fluorine is much more electronegative, meaning that it has a much greater tendency to attract electrons. The electrons are going to spend more time with the fluorine than they are going to be with the hydrogen. So the electron bonding pair is not evenly shared. And so this molecule is no longer symmetrical. It's not symmetrical, and it's going to be polar. Now this builds on the shapes of molecules that we talked about in the previous video. Molecules with no unshared electron pairs are always going to be nonpolar. So for example, BF3, CH4, PF5, SF6, none of these have any lone electron pairs on the central atom. Alright, so let's look at the first example, BF3, which is an example of an AB3 molecule, which is trigonal planar. Okay, looks like this. It's planar, it's flat. So you might want to say, well, you said, wait a minute, the atoms aren't the same. This is a boron and this is a fluorine. So why isn't it polar? Because we have this fluorine pulling electrons this way, and this fluorine pulling electrons this way, and this fluorine pulling electrons this way, and these all balance each other out. This pull is balanced by these two, okay, because it's totally symmetrical. We've taken a circle and divided it up into three even pieces, bond angles of 120. A good rule of thumb is that if you can take a molecule and spin it around the bonds, pretend like it's a propeller blade and spin it around the bonds or spin it around some imaginary axis, and if it's balanced, then it's symmetrical and it's nonpolar. So for example, we could spin it around this CC bond, spin it around some imaginary axis perpendicular to the boron like this, and it's symmetrical. Okay, because you've got these divided up into 3 bond angles are all the same. Circle divided into 3 pieces. You could also spin it around this way, and it's balanced. Okay, that's balanced. So that's symmetrical. Okay, same thing for the AB4 molecule. Same thing for the AB4 molecule. CH4, which is an AB4 molecule, this tetrahedral. Same thing. This is symmetrical. We can spin it, try to spin it, imagine spinning it around any of the CH bonds, and it's going to be symmetrical. Okay? Same thing for the AB5 molecule, PF5, which we said has trigonal bipyramidal geometry. Now remember, in a trigonal bipyramid, you have trigonal bipyramidal molecule, you have the 2 axial positions and the 3 equatorial. So here are your 2 axial positions, here and here. Those 2 are opposite one another. They balance each other out. So this pull is balanced by this pull because those are opposite one another. And these 3 are arranged evenly in a circle, so they cancel each other out, right? So this molecule is completely symmetrical. That makes it nonpolar. And last, our sulfur hexafluoride, AB6, same thing. This is symmetrical. Okay, so we have this fluorine pulling electrons this way, but it's opposed by this fluorine pulling electrons this way. And this one is opposed by this one, and this one back here would be opposed by this one. So all the effect of the electrons pulling, of the fluorines pulling electrons away from the sulfur are all canceled. So it's completely symmetrical, so it is nonpolar. Now, a molecule with a single unshared electron pair will always be polar. Now think about why that is. Because there's nothing to balance it out. There's no way for a molecule with a 1 unshared electron pair to be balanced. If you had 2 or more, maybe. Depends on how they're arranged. But if you have just 1, it's always going to be polar because there's nothing to balance that out. So, for example, ammonia, NH3, which was our example of an AB3E molecule, which we said has trigonal pyramidal geometry, looks like this. So you got 3 atoms and a lone pair. Well, you might say, okay, well, if you spin it here, it's balanced, and that's true. But if you spin it like this, around this bond, it's not balanced. This is going to be like a fan blade where one of the blades is either missing or is much bigger or smaller than the other 2. You spin that around, that's not balanced. Okay, so it is going to be polar. All right, so SF4, once again, we classified this as an AB4E molecule. So once more, you have 1 unshared electron pair. It's a trigonal bipyramid where you have an equatorial position occupied by the lone pair. Now, the axial positions, the 2 that are opposite one another, would still cancel each other out. But the equatorial positions are no longer balanced, because 2 of them are atoms and 1 of them is a lone electron pair. We try to spin that around, and again, it's going to be like a fan blade where one of the blades is either, missing or much bigger or smaller than the others. That's going to be polar. Okay, so a molecule with a single unshared electron pair is always polar. AB3E, AB4E, AB5E, all of these have that single unshared electron pair. Now, what about molecules with 2 or more unshared electron pairs? It depends on the symmetry. They can be nonpolar if they are symmetrical. So for example, we'll look at water. Okay, so we classified water as being an AB2E2 molecule. Two attached atoms and two lone pairs, right? So here's our oxygen. Here's our oxygen, and we have the two hydrogen atoms, and we have the two unshared electron pairs. Well, those electron pairs are not balanced. If we try to spin this around, again, let's try to spin it around one of the bonds, the CH bond. We try to spin it around. It's like, again, it's like a fan blade. All these aren't the same. That's going to wobble as we try to spin it. Okay, and you may say, well, we could try to do it here, spin it around the lone electron pair. It's the same thing. You're never going to be able to get all three of the like atoms or like objects the same. Okay, so it's polar. Okay. Now if we look at ClF3, we classify that as an example of an AB3E2 molecule. You have three atoms and two lone pair electrons, and we describe this shape as being T-shaped. Okay, the lone pairs occupy two of our equatorial positions. Okay, so the axial atoms, the two axial atoms, still balance one another, but the equatorial positions are not balanced because we have two unshared pairs and one atom. We try to spin that around. Again, that's going to be like a fan blade, where one of the blades is a much different size or a much different mass, or it's bigger or it's smaller than the others. It's not balanced. Okay, it's not an even distribution of electrons. In other words, this pull is not balanced by these. Okay, so it's going to be polar. Last two examples. Okay, last two examples. So XEF2 and XEF4. So XEF2 we classified as being XEF2 we classified as being an AB2E3 molecule. Okay, it's described as being linear shape. It looks like this. So now this is different because you have three lone pairs occupying the equatorial positions. So you have the two axial positions are balanced because these two atoms are opposite one another, and the equatorial positions are balanced because we have the same thing on every pair. We have on every side we have an unshared electron pair. This is balanced. Okay, so it is nonpolar. And the same thing for XEF4. We classified this as an AB4E2 molecule. You have four attached atoms and two lone pairs. Now if we look at this model, the two lone pairs are opposite one another. They're 180 degrees apart. Two lone pairs 180 degrees apart. They're opposite, right? So the pull of this electron pair is balanced by the pull of this electron pair. And the four atoms are in a plane, hence the name square planar. Four atoms are in a plane. The bond angles are 90 degrees apart. That's a symmetrical distribution of atoms around the central atom, right? So this molecule is definitely nonpolar because it is symmetrical. All right, so what are some of the consequences of molecular polarity? Why would we care about whether a molecule is polar or nonpolar? Well, polar molecules are going to have partial charges due to the uneven distribution of electrons, right? The two atoms are the same, there won't be any partial charges. But if atoms are different, then you'll have partial charges on the molecules. All right. So as a consequence, polar molecules will have a dipole moment. This is the magnitude of the charges on the molecule multiplied by the distance between them. Okay. Polar molecules can be influenced by electric fields. Okay, because you have charges on the molecule. And last, and possibly most important for our purposes here, polar molecules typically have higher melting and boiling points. And this goes back to our first statement up here. They will have partial charges due to the uneven distributions. So let's say we'll have a positive charge on one molecule becomes attracted to a negative charge on another molecule, so you have forces of attraction between the molecules. The greater those forces, the higher are going to be your melting and boiling points. So polar molecule, we'll talk more about that, but polar molecules tend to have higher melting and boiling points, and that's because of the partial charges. All right, so that wraps up this video.